Here we consider the spherical capacitor. We have an inner radius A, so that is a charged sphere with plus Q on it. And we have an outer thin shell, also a conductor, with a charge. Hard to draw. And it has a radius of B, and it has negative charge on it. This minus Q. We're going to consider the potential at infinity to be zero, like we always do with point particles. And when you have a capacitor, it's really just two conductors near each other with some potential difference and some opposite charge. So we've actually been given the charge. To get the capacitance, we really just need to keep in mind that C delta V equals Q. So we can calculate the potential difference between the outer conducting shell and the inner conducting sphere. Once we have delta V, we have Q, and we'll get the capacitance. But the problem takes us through a few intermediate steps. So let's look. I would start by remembering a few things. First, remember that for a charged sphere, and actually in this case, whether it's a conductor with charge on its surface or it's got charge throughout, in any case, we have any kind of a charged sphere that acts like a point charge if you are outside. So if we calculate anything outside of this charged sphere, we can just say it's plus Q sitting at the origin. Let's see, for a spherical shell, here's another bullet to remember. Spherical shell of charge. Well, if you're outside, again, it acts like a point charge. But if you're inside, E equals 0. I don't think we proved that in this class, but I'm telling you it's true. We didn't do enough Gauss's law to prove it. And then one more thing, if you know you're inside something, and you know that E equals 0, then you also know that the potential is constant. Because the electric field is the time derivative, or the spatial derivative of the potential. So if the electric field is 0, this isn't changing. It's a constant. So just because E is 0 doesn't mean the potential has to be 0. It's just that the potential isn't changing. Okay, so with those reminders, we can then do the problem. And I actually think it's easier to do part B first. It was written first with part A, but let's think about part B. Part B is what is the potential on the shell. It actually says inside surface of the shell. For now, let's just ignore the thickness of the shell, and I'll explain what it meant. Okay, so the potential here, or anywhere, is really just the sum of the inside plus, well, we'll say the sphere, pH, plus that of the shell. It's two charge distributions. The potential is just the sum of the potential from each of them. Okay, so let's look at it then. The potential due to the sphere at this point, well, we're outside a charged conductor, so we just treat it like a point charge at the origin. So it's just the potential of a point charge is KQ over R. So K plus Q over R, but R is how far you are from that point charge. So the radius in this case is not to A, it's to B. This is how far we are from the place where we're treating this as a point charge. So it's KQ over B. That's the potential due to this thing. Now what's the potential due to this? Okay, so now I say the potential at infinity is 0. If we're outside of this charge distribution, it acts like a point charge at the origin. So we could calculate the potential to the outside surface right here. And that would be K, Q, and over R, well again, that's B. Actually, it's slightly bigger than B, because we're slightly outside, but we have a thin shell, so we're going to call it B. And you could say, well, that's the potential here on the outside, not the inside, but remember they're the same. Remember, the potential doesn't change inside of a metal. So if you go from the outside to the inside, potential is the same, so it doesn't matter. Right? You could say, but the KQ over R, the R was B, but in this case, the charge actually sits on the inside surface because it's attracted to the positive. So So I have an answer for everything. But those are all details not to worry about. We're treating it as a thin shell, so don't worry about the thickness. So from this, you'll see something kind of weird, is that we get 0. Right? The two potentials just add up and cancel. So that seems unusual, but it's actually okay. It's just sort of a coincidence. The potential is 0 at infinity, and as you approach, imagine you're at infinity. What are you approaching here? You're approaching some positive charge and some negative charge right on top of each other. So they cancel. You see essentially nothing until we get inside. Right? Let's imagine we went outside the shell. We'd get the exact same thing. K plus Q over B, K minus Q over B. So this thing creates no potential outside, just like a parallel plate capacitor creates no field outside. Okay, so that's part B, 0 potential. That's how you get here. Part A asks for what it is at this surface. All right, now what is it at the surface of the sphere? Now maybe this will be different. Let's add it up the same way. The potential is the potential of the sphere plus the potential of the shell. Right? The sphere, well, we're outside of it if we're right at the surface. So it's like a point charge, all that plus Q, right there at the origin, K plus Q over R. In this case, we are a distance A away, so it's over A. So KQ over A. Now what is the potential here due to this distribution of charge? Well, it is a spherical shell of charge. The E field inside that it creates is 0. Okay, this will create a field inside. But we're just treating them completely independent. Let's imagine only this shell is here. So that creates 0 field inside, which means the potential will be constant inside. The potential won't change. So the potential here is the same as the potential here. We already said what that is. That's K minus Q over B. Right? It's the same thing it was here. So we're going to say K minus Q over B. I got that just from the property of an empty shell of charge. Empty shell of charge, E field inside is 0, and the potential inside is constant. If you're only considering the shell. This is going to change those values, but we are adding these two things as superposition. We already put in what this sphere does. Now we're putting in what the shell does. All right, so if we wanted to write that a little nicer, I guess we could say it's KQ 1 over A minus 1 over B, because that minus went in front of the A and the B. All right, so there is the potential on that surface. Remember, this was at the surface. The value of this surface equals the value of the surface. And then finally, part C is what is the capacitance? I believe that's what it is. Yeah. So one thing to remember is if you calculate a capacitance correctly, it only depends on geometry. We put a Q on here, and we calculate the voltage, and the value of the charge and the value of the voltage will change around. But when you calculate the capacitance, that should all cancel out, and you should just get something geometric. So let's see if that happens. C is Q over delta V. All right, the Q we have is the charge Q that we use. So we just call it Q. And delta V is this, K, Q, 1 over A minus 1 over B. Right? And sure enough, there go the Q's. And all that's left is a constant of the universe and geometry, 1 over A minus 1 over B. So you could write this sort of an ugly way, 1 over K in the denominator, 1 over A minus 1 over B in the denominator. That's not real pretty, so you'll usually see it written by simplifying it by multiplying by 1. 1 in the form of A times B over A times B. Because that will give you A times B over K. Now A times B over A is B, minus A times B over B is A. See, doesn't that look prettier? But the key is it only depends on the geometry. It doesn't depend on how much charge you put on it.